think I might only have time for question 7, but anyway, if I have time for question 8, then I'll just say so. Anyway, let's go. So draw a Nyquist plot to indicate a stable closed-loop system and an unstable system. So you need 2 diagrams. Be very careful when you read it. Alright, and for the stable system, mark the gain margin, phase margin, vector margin. Explain meaning of the gain margin and these things. Alright, so how do we do this? So let's draw something for the stable system. Alright, you have a Nyquist plot over here. It should be phi, right? Maybe I should draw something better. Maybe I should draw something like this. Okay, that will illustrate a more understanding rather than just now that picture. Alright, so we'll have a unit circle also. Alright, over here. Alright, I should enlarge this Nyquist plot. Okay, for the first one, the gain margin. Alright, let's zoom in. If you still remember, the lambda is over here. Alright, this range is telling you that this is lambda. Okay, this whole thing over here is telling you 1 over lambda. Or we can call this whole thing your gain margin. Okay, and therefore the gain margin is something to tell you the distance between your Nyquist plot and -1. Alright, so it's just this distance. Alright, if you don't believe me, you can state that the gain margin indicates the additional gain by which the L0 may be multiplied, so it reaches the -1. Right, this is more in a more detailed and exact way. I would highly suggest you remember this one. But the meaning is just simply, if you were to further increase this, this L0, this is the L0 Nyquist curve, right? If you were to multiply by k, because normally you have a certain transfer function. So transfer function has a certain constants, right? Because you can multiply to enlarge it or what, or make it bigger. So this enlargement may actually cause it to go into this way. So it's somewhat multiplied. So this tells you that how much you can multiply before you reach -1. That's the meaning of that. So how much you can multiply, and then it reaches here. You can also multiply when it reaches here. As long as it doesn't cross -1, you should be safe. Okay. For the gain margin is simply telling you the distance at the real axis from this point to this day. Alright. So this means that the larger your gain margin, the better, because you're further away from -1. Alright, so gain margin is preferably higher the better. Okay, the next thing is phase margin. The phase margin is over here, as you can see. This is the cross section between the Nyquist plot and the -1 encirclement over here, right? So therefore this is somewhat the angle, call this the theta. Okay, we also have a phi angle, we call this the phase margin. Alright, so the same thing is that -180 plus theta is equals to minus phi. Alright, so your theta itself over here, which is over this side, if it's 50 degrees, although this doesn't look like 50 to you, but maybe about 120 lah. Alright, so you have a somewhat -60 degrees. So this tells us that we have 60 degrees more. Alright, this portion over here is 60 degrees. We have 60 degrees more to reach -1. Alright, so we have a certain angle before we go to unstable. Alright, so this is somewhat telling you that how much angle can you take in order to go unstable. And therefore for the phase margin explanations is how much additional phase delay you can add to your L0, which is your Nyquist plot, to reach the critical condition -1. Alright, so therefore you need to also understand additional phase delay. Alright, so this for the gain margin is which L0 may be about multiplied. Additional phase delay to where's my pen? Additional phase delay added to L0. Alright, so these are the two keywords that I highly suggest that you should take it down. Alright, the vector margin is something very different. It's the distance between your -1 to the nearest distance to your any point of your Nyquist plot. Alright, so the vector margin is somewhat very deep. Alright, so somewhat is this distance. Alright, how does vector margin comes about is when you're talking about a very low, you have -1 over here. Talking about where you have a very low gain margin and phase margin. As you can see, the distance for your gain margin is so freaking high. Alright, for your angle over here, for your phase margin is also so freaking high. Alright, but however, for the vector margin, as you can see, this part over here is really seriously very short, and it's going towards unstable. And therefore for gain and phase margin, you can't measure, your vector margin is going to take place. So this is the key understanding you need to know for the phase margin, the vector margin. Alright, so let's use this graph since we already draw this. Okay, so where's my arrow? Yeah, this thing over here. We call this the vector margin, or 1 plus CP naught. If you still remember, this is your S inverse. Alright, this is your sensitivity function, 1 over your sensitivity function, if you still remember. It's telling you the distance from -1 to your CP. That's all. Okay, the vector margin is denoted by SM. Alright, vector meaning S margin. Alright, this M is margin. This is the distance from the point -1 to the closest point on the plot of L0. Alright, and somewhat you also want your vector margin to be high. So as a summary, we just want to let you know that the gain, phase, and the vector all must be high. All their margins must be as high as possible in order to be stable. That's just the understanding. Okay, but we only draw about the stable one. We haven't drawn the unstable one. Alright, so for this case, you can illustrate that this picture over here is considered stable. Okay, because your gain, phase, and vector margin are all kind of stable. So what about the unstable one? Let's just draw it up. We have a -1 over here. Alright, you may have something like this. This is considered unstable. Alright, you may also draw a -1 over here, and then you may have something like this. This is also unstable because you already encircled the -1. Alright, and just to let you know, if it happened that you forget or what, this is only one side of a Nyquist plot, meaning you are plotting from frequency 0 to infinity at this point. Alright, so you can also plot from this point. You have a symmetry type of picture, which is something like this. So you have something like this, which is going on the other side. So this is from 0 to -infinity frequency. Alright, it's going in this direction, and therefore normally we draw this, we indicate the arrow over here, stating it's going in this direction. So it's going from here all the way to here. Alright, for infinity to 0. that should be good. From infinity to 0, and then from 0 to -infinity. Okay, something like that. Okay, so this is something that you may need to also know. Alright, so you can draw whatever thing as long as it is considered unstable. You should be fine. Alright, so yeah, later we have used quite a lot of time. Therefore next section we will talk about the question 8. Alright, and therefore let's see you there.